While there are a number of stories as to how it happened, the one I've heard most often involves a kindly shopkeeper who allowed children to play. In my mind's eye, it's a sunny day on the streets of Middelburg in Holland. The shopkeeper, a spectacle maker by trade, is a genial man who keeps his door open and some of his wares out on a counter for those who want to examine the quality of his product. The small pieces of glass are ground into different shapes, some thicker in the middle and thinner at the edges, while others are the opposite, thinner in the center. The former are usually for the older customers, for whom reading the news sheets, pamphlets, and books that circulated through the city had become difficult. The latter made for those who had trouble seeing out to a distance. The lenses were either circular or half-circular, as those were the easiest to work with and to set in frames of metal. On sunny days, the neighborhood children would come to his shop. The lenses that were thicker in the middle would concentrate the light of the sun, and on particularly bright days, cause a leaf or a piece of paper to begin smoking. The shopkeeper, when there were few customers, would loan the children a few lenses, perhaps chipped through handling or imperfect in manufacture, to play with in the streets. You can imagine it in your head, can't you? Mr. Hans, can I have a lens? Mr. Hans, what does this one do? Mr. Hans, how big of a magnifying glass do you think you'd make if you had all the glass in the world? And then one day, Mr. Hans, come see, I've made things bigger. No one really knows how Hans Lippershey first came up with the idea of putting two lenses in line, in the right combination. But there's a chance that he was prompted when the children playing with the lenses of his spectacle shop showed him how to make objects that were far away look like they were a lot closer than they really were. What we do know is that in 1608 he applied for a patent for a device with two lenses, one thicker in the middle and the other thinner, placed into a pair of cylindrical tubes, one sliding inside the other, that magnified distant objects. For the seafaring Dutch, this was an innovation of profound importance. Soon as the word got out, the other major seafaring nations began to hear word of the invention, among them England and Venice. In 1609, the ruler of that Italian city, known as the Doge, desired to see one for himself in order to decide if he needed to create a way for Venetian merchants and war vessels to have a ready supply of the instrument to stay technologically competitive. He was allowed to see a version of the device and was duly impressed by its ability, and so he began to consider entering into negotiations to have a number of them made in the Netherlands and shipped to him. It was at this point that he was told that there was a man in Padua, a natural philosopher and mathematician there, who could make them locally. The Doge, eager to source the technology from within his territory so as to avoid the possibility of a later embargo, requested that the philosopher, a man with the same first and last name, provide a sample of his work. And so it was that Galileo became familiar with the instrument that would come to be known as the telescope, an instrument that, when used in a way for which it had not been designed, would vault him to fame in Italy and beyond, and would put him on a collision course with the forces of Aristotelianism he had only sparred with up to that point.
Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a many-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery.
Series 3, Finding Our Place. Episode 18, The Starry Messenger. When last we left our intrepid natural philosopher, Galileo was working out the details of a radical new idea of motion. In describing this, I neglected to make an important point. one that is foundational to the work he will do later. As we discussed much earlier in this series, for those who thought in terms of Aristotelian sublunary physics, i.e., the description of the nature and causes of motion here on Earth as opposed to those things in the heavens, there were two types of motion: natural motion and forced motion. The former was the motion of an object seeking its natural place, either by moving upwards if it possessed levity or lightness, by being made of air or fire, or downwards if it had gravity, through consisting of air or water. The other form of motion was forced motion, as was the case of an arrow being shot from a bow or an object like a box being pushed along a tabletop. In his work, Galileo contradicts this picture in several ways. First, he completely rejects the idea of levity or lightness, and he replaces it instead with what we think of as specific gravity or density. All objects tend to fall, he said. It was just that some objects, due to having a higher specific gravity, would travel through media that had lower specific gravity. This would explain why oil floated on vinegar or iron shot fell through water. Second, as we mentioned, he rejected the idea that both natural and forced motion had to be constant velocity motion. Finally, he put forward the idea that there might be a third type of what he called intermediate motion. The idea here was that there was a type of constant velocity motion wherein there was no force required to keep an object moving. Galileo used two examples for this. The first was the idea of a ball rolling across the surface of a frozen lake, while the other was that of a river continuing to flow even down the slightest grades. This intermediate motion idea has a great deal in common with the impetus theories of Buridan and Erasme from the 14th centuries, though it is fairly clear that Galileo did not know of those ideas. While this idea will not be fully developed at this earlier time, it will be the basis for Galileo's later idea of inertia that will prove so instrumental in physics a few years down the road. We will discuss those in due time. The focus of this episode will be on Galileo's work in astronomy, that thing he is best known for, perhaps apart from his trial, but also the work that is probably the least scientific in some ways. His work on the motion of objects was almost completely experimental, in the sense that he was able to control all the aspects of the systems he was studying, and was able to come to generalizable conclusions that could be stated in a mathematical form based on the process that we discussed in last week's episode. In his work on astronomy, however, he was not able to control the system being studied, and so he reverted from what might be called experimentalis to something that would have been scientia, or observation as it was known. While his work on the motion of objects, as well as his work on tides, had led him towards accepting Copernicanism, it was the new star of 1604 that seems to have sealed the deal. If the new star of 1572 is sometimes known as Tycho's star, the event in 1604 is usually called Kepler's. Both of these stars, or novae as they are called, are now known to be astronomical events involving the cataclysmic release of energy that can either be called a nova or a supernova depending on the specific details of the eruption or explosion off of a star. At the time of Galileo, however, and for centuries afterwards, the nature of these sorts of events was unknown, and so they were just supposedly apparitions in an unchanging celestial realm. As we discussed, in 1572, Tycho had shown that the events had to have taken place beyond the sphere of the moon, using instruments inferior to the ones that he would eventually build. However, in 1604, this new star offered a chance to test that idea once again, in many cases with instruments that had been developed after Tycho's golden decade on Avene, and so were much, much better. Galileo made a number of observations of the new star, and wrote to other Italian astronomers asking them to do the same. Across the Alps, Kepler too mustered the astronomical community near Prague to make similar observations. both men, independently of each other, came to the same conclusion. As was the case in 1572, this new star was also located well beyond the sphere of the moon. In Prague, apart from the scholastic institutions there, and protected by his position as the imperial mathematician, Kepler encountered little pushback to announcing this result. Galileo, on the other hand, received a very different response from his colleagues at the University of Padua. In announcing his findings, Galileo gave 3 well-attended public lectures that detailed the observations made and the results that could be derived from them. He then announced the conclusion of this work. Aristotle had been mistaken. Just like the terrestrial realm, the celestial domain could change. The quintessence, or the ether as it was sometimes called, wasn't eternally the same. It could, apparently, come together in some way to form a new star for a period of time. This was a profound result, and a strong conclusion to draw from that result, and it shook the Aristotelian world of the scholastic universities in a way that is hard to understand now. As you might imagine, there was a response from those deeply invested in that worldview. The senior professor of philosophy at Padua, Galileo's colleague and friend, Cesare Cremonini, responded by having one of his students publish a book refuting Galileo's work. Now, it was really difficult to sort of refute the observations, as they were the same that were used to establish the supposedly unchanging motions of the heavens in the Aristotelian model. So Cremonini, through his demiurge, claims that the rules of measurement on Earth didn't apply when it came to making heavenly observations. While parallax measurements made through air could be counted on to arrive at certain reliable conclusions, the nature of the ether rendered such methods reliable over the vast differences being considered, or at least that was the argument against Galileo. To reason correctly, he said, one had to take into account the Aristotelian principles that applied only to the quintessence. I think that it's at this point that a real shift takes place in Galileo's thinking. And I want to emphasize here that this is my idea and my idea alone. It is nothing more than the opinion of a guy who's done a lot of reasoning and tried to figure out why what happens going forward happens. Up to this point, I think Galileo is involved in the traditional scholastic dialectic process of debate and disputation. He is, in a sense, doing what the natural philosophers in Paris and Oxford had done in the 14th century leading up to the Great Mortality. Like them, he has found real problems with Aristotle's terrestrial physics, and he's not alone in this time. Other natural philosophers in Italy are coming to some similar types of conclusions. As such, his disagreements in this area are scholarly in nature, and while there is certainly a good bit of ego involved, everyone is willing to accept that the goal is to get at the truth, and that's what everyone's trying to do. However, as he does his experimental work on the motion of bodies, I think Galileo reaches the same conclusion Roger Bacon had some 300 years earlier, that the process of prioritizing knowledge gathered by reasoning, Aristotle's episteme, over that kind of knowledge arrived at through experience, what Bacon calls scientia experimentalis, is just wrong. And that just as it got Bacon into more than a bit of trouble when he said that his process arrived at a more reliable knowledge than the use of reason did, Galileo's similar assertions going forward are going to create a break that will lead to him ending up under house arrest. Cremonini's response, I think, makes Galileo realize that the Aristotelian paradigm is fundamentally broken. So broken, in fact, that the philosophers who defend it will go to ridiculous extremes to get around the obvious sort of what I would call observational inconsistencies that arise. In other words, I think Galileo loses faith that Aristotelianism is in any way a path forward, and that the Aristotelians are really interested in getting at true knowledge. In my head, I can sort of see Galileo reading the book by Cremonini's student and saying, "Are you kidding me? Is this really your response? Up until now, you've been just fine with the methods of measuring the motions of the heavens, but now that they give you a result that calls into question the philosopher's view of things, you question them? Really? That's your response? Here we stand on the verge of some really exciting and new stuff, and you're going to say we can't really measure stuff? Unbelievable. Now again, this is just my opinion, so take that for whatever it's worth. But I think it explains a lot of what Galileo will do going forward and why he writes so dismissively of those who continue to cling to Aristotle's picture of the world. What we do know is that Galileo writes a response, a little dialogue between three peasants discussing these ideas. The dialogue is written in the local Paduan dialect of Italian, and it's a brilliant piece of the form of rhetoric wherein the ideas of a supposed learned man is mocked by the simple common sense reasoning of one who works the earth. In it, one peasant asks the other, what does a philosopher know about measurement? Isn't measurement something done by mathematicians? The other responds by agreeing that it is mathematicians who should be trusted with the measurements, and it didn't seem as if they cared whether the thing being measured was made of quintessence or of polenta, as the substance wouldn't change the measurement of distance. What Galileo's saying to Cremonini here is that, what do you know about measuring things? Have you ever been inside of a lab? Have you ever used a sextant or a quadrant? I invented a new type of military compass. What have you done? I've just spent the last 10 years of my life figuring out how to make measurements of moving objects. How about you? You're using ideas from a guy I've shown to be wrong about things to tell me I'm wrong about the thing that shows him to be wrong again. How does that work? In one sense, it's a devastating critique, but only if you happen to agree with Galileo on the value of experiments and measurements made by the senses. This is a good place to talk about a reality and a really interesting point made by David Wooten in his biography of Galileo titled Galileo, Watcher of the Skies. When one looks at Aristotelianism, it should be recognized by this time that the paradigm only bears a limited resemblance with the original writings of the great philosopher himself. While most of his conclusions have been accepted as unassailable facts, the methods of arriving at them, the sources of knowledge, have been modified. This was first done in the Thomistic synthesis of the 13th century in response to the condemnations of 1270 and 1277. However, the bigger influence at this point was the inclusion of Platonist ideas stemming from the rediscovery in the West of Plato's writings after the fall of Constantinople. As such, while Aristotle himself felt that the senses were a valid guide to the use of reason, Plato's questioning of that premise led the scholastic thinking of the 16th and 17th centuries to reject the validity of sense experience to inform reasoning, especially when that came to God. This was also especially true for the sense of sight, which was held to be particularly susceptible to being tricked. If you think of the number of fascinating illusions that rely on tricking the apparatus of visual perception, from the idea of perspective in two-dimensional art to a whole variety of optical illusions involving comparing the lengths of two objects or the colors of two squares, this skepticism about seeing is understandable. Galileo, on the other hand, with his emphasis on experiment, was claiming that the use of the senses was not only valid, but a powerful tool for understanding the natural world. Today, living in a culture saturated with visual stimuli, we take this for granted. But that shift was beginning at this time, and Galileo was one of those responsible for helping it along. It is likely no coincidence that the phrase, seeing is believing, at least in English, dates to 1609, the year that Galileo will first point his telescope to the heavens. This emphasis on sight is first found in Galileo's earliest work on the hydrostatic balance and on his work in calculating centers of gravity, but it will pervade all of his work, and the difference of opinion regarding the reliability of the senses will factor heavily into the debate about Galileo's telescopic observations in the future. In 1607, while continuing his work on moving bodies, Galileo would become embroiled in a priority dispute regarding his work. A year earlier, he had published a manual to go with his military compass, or sometimes it's called a sector, and had dedicated the work to a prince of the Medici family who had ruled Florence in these years. After his book came out, another engineer, Baldassare Capra, published a Latin version of the work that was plagiarized and claimed that any other work was a copy of his original ideas. Now this was a big deal, as it made it look like Galileo might have dedicated a dishonest piece of treachery to the prince. As in Tycho's case, Galileo was forced to accumulate evidence that he in fact was the original author and then present it in court, a case that was eventually settled in his favor. Like Tycho, though, Galileo would become much more distrustful following this incident, something that would not work in his favor in the future. Sometime between 1607 and 1609, Galileo was able to figure out that the path of a projectile was parabolic, a topic that is a staple of any first-year physics course today. He also seems to have worked out the idea of inertia in much greater detail. This was compiled in a manuscript that was being prepared for publication when news arrived from Holland of a new instrument. Galileo's friend, Paolo Sarpi, had heard about it, and Galileo realized that if he could figure out how to make better versions of the instrument, he could sell them for a significant amount of money. Two notes here. First, I wish we had time to go into the life of Sarpi. He's one of the most interesting figures in Italy during this time, and his work in science, medicine, politics, and theology could fill several podcast episodes. Unfortunately, it's tangential to where we're headed. Second, at this point in his life, Galileo could be said to be deeply immersed in what we might call today the rat race. His salary at Padua was reasonably good, but his expenses are significant, often outpacing his salary. So big is the discrepancy that he's forced to set up an entire side business of taking in and tutoring students in military sciences, an enterprise that made him up to 3 times more than his academic salary did. Moreover, as he became more enmeshed in his research on motion, he began to experience the resentment many modern academics at research institutions feel. The tension between giving time over to teach and the time needed to research. While every scholar deals with this differently, it seems pretty clear that Galileo really started to resent his teaching time and was looking for a way out of having to cover the Aristotelian curriculum he was coming to despise. So, when word of the telescope from Holland finally reached his ears, he became interested in seeing if he could, in his words, reinvent the thing. Given the limited number of lens combinations, he likely hit upon the design pretty rapidly. The problem was that since he had used lenses commonly found in a spectacle shop, the magnification was only about 3 power, half of that found in the instruments beginning to arrive in Tuscany from Holland. Moreover, as was the case with the Dutch telescopes, the image quality wasn't the best. Due to an effect known as chromatic aberration, caused by the fact that glass bends blue light a little more than it does red light, objects viewed through a telescope had a sort of rainbow of color around them. This is where Galileo's experience as an instrument maker from his compass or sector work comes in handy. Over the course of the next few weeks, he quickly refines the design of the instrument and improves the magnification first to 8 power, comparable to a modern pair of binoculars, and then 20 power. When demonstrated for the Venetian government, Galileo's telescope was superior to what was coming in from Holland, both in terms of magnification power and image clarity. From what I've been able to find out, it's not entirely clear how Galileo was able to achieve these successes when it seems that the methods and technologies should have been available to almost anyone, but we do know that for about 20 years, Galileo's telescopes would be the bleeding edge. At this point, I'd like to take a momentary digression to talk about telescopes just a bit. We really don't know who invented the first telescope. Spectacle lenses were developed in the middle of the 13th century, so it's a bit puzzling that it would take 350 years for someone to come up with a combination of 2 of them that would magnify an object. There are a number of references in various pieces of literature predating this 1600 time period that would suggest that others had stumbled upon the technology, but it's clear that if they did, they didn't follow up on it. So why is that? Well, there are 2 answers, I think. The first has to do with that bias against visual perception that we've already discussed. If things, once invisible, due to being too far away, were now made visible by the lenses, how could one be sure that what was going on wasn't being seen due to a trick created by those lenses rather than being something real? In an era when seeing wasn't believing, that's really an important question. The second reason, I think, has to do with how glass worked to bend light. The phenomenon is known as refraction, and had been known about as far back as at least ancient Greece. It had been a subject of research, as we discussed, throughout the Hellenistic period, and then again in the work of Al-Hatham up to the period of the scholastic natural philosophers in Oxford in the persons of Robert Grosseteste and Roger Bacon, who was one of those who may have experimented with an early telescope. If you've ever placed a straw in a glass of water or a pole in a swimming pool and seen the phenomenon where the straw or the pole seems to bend as it passes through the surface of the water, that's refraction. The straw doesn't bend, of course, but the light coming from it and passing back through the interface between the water and the air does. If you have two interfaces, as would be the case with a piece of glass with a thickness, the light can bend twice. And if the surfaces of the glass are curved, the light can either be bent so that it all converges to a single focus, as it is called, or so that it spreads out, looking like it's all coming from a single focus. The first case is called a converging lens, and it's what you have in a magnifying glass most of us probably use to focus the sun's light on leaves or poor unsuspecting insects. The second type of thing there is called a diverging lens, and it's the kind of lens you have in your glasses or contacts if you're in fact nearsighted. Nowadays, when we look at lenses, they're made with extreme precision and uniformity. The materials have no imperfections or irregularities that would make something seen through them look wavy or distorted. Moreover, because we use methods of producing heat that don't require the burning of some material such as wood to melt the silica into glass, there's no smoke or soot that can get into that molten material to darken the final project. None of this was the case in the late medieval period. Glass was smoky, warped, and filled with bubbles, and so were the lenses. As such, any telescope someone in the 13th century might have produced would have created dark, distorted images that would have been hard to make out. Hence, I think the references made by those earlier writers probably were people who had figured out a good lens arrangement and thought solving the problems with making better lenses would be easy. Unfortunately, the glass-producing technology of their time wasn't up to the task. By Galileo's time, especially in northern Italy, that had changed. Galileo had access to better glass-making technology capable of making clearer glass with fewer irregularities. Lenses could be made thinner, thus introducing less distortion into an image, thus allowing for greater magnification. Galileo seems to have been able to grind the shape of the lens with much higher precision than was typically done by spectacle makers, and so his telescopes were just plain better for a long period of time. This is not to say, however, that they were perfect. Even with the advances in lens production technology, the clarity of images produced when looking through one of Galileo's telescopes wouldn't begin to approach that found in even the most commonly purchased binoculars or telescopes made today. One last point that should be made here before we move into what Galileo did with his telescope. When you go to your local department store or online retailer to buy a refracting telescope, you can't actually get one made according to Lippershey's design, the one that Galileo reproduced. Their type of telescope used a converging lens as the objective and a diverging lens as an eyepiece. This had the advantage of producing an upright image, but the disadvantage of creating a lot of distortion. If you buy a refracting telescope today, its design is based on the type of telescope invented by Johannes Kepler. In this design, two converging lenses are used. This produces an inverted image of much better quality. Of course, all of this neglects what are known as reflecting telescopes that use one or more mirrors to produce an image, but that's a story for another time. So, after about 4,000 words of build-up, let's talk about what Galileo saw when he decided to place one of the telescopes he was building on a tripod. Before I do that, however, let me just say one more thing. Galileo's not the only person to do this. There are others who will have the same idea and it will reach a number of the same conclusions as he does. We'll discuss this in a bit more detail in later episodes. The first thing Galileo seems to have done is to look at the stars. What he finds is that they don't get bigger. Why is this a big deal? Well, what it means is that the attempts to measure the angular sizes made by Tycho were an error, which means that his argument against Copernicus, that the stars would have to be enormous in size, were wrong. It also tended to lend support that things really were a lot farther away than folks thought. He then looked at the Milky Way and found that it was resolved into a very large number of individual stars, something many had suspected for some time. The first really big discovery happened when Galileo pointed his telescope at the moon. By being able to resolve features on the moon much more clearly, he was able to confirm an idea that had been floating around since at least 1606, that there were mountains on the moon. This is the first significant result that would counter the ideas of the Aristotelians. For them, the heavens and all that were part of them were perfect, and thus were constructed out of perfect spheres. The quintessence, or ether as it was sometimes called, was so different than terrestrial matter that it didn't allow for anything else. Everything had to be this sort of perfect form. By observing the shadows cast by the mountains and how they changed, Galileo was able to say that, like the Earth, the moon had terrain. He even attempted to use the length of the shadows in some trigonometry to arrive at a height for the mountains, something that I think he got to be around 4 miles tall, if I recall. Finally, he turned the telescope to the planets, and it was here where he found the greatest surprises. First, unlike the stars, they did resolve themselves into disks. This was an indication that not only were the planets places, things if you will, rather than disembodied entities as some thought, but that like the moon seemed to be, they might be made of the same stuff as the Earth. Of these observations, though, the most sensational were those showing the 4 stars that seemed to orbit Jupiter. This was a really big deal. If you're an Aristotelian, one of the things you've hung your hat on is that the Earth, or at least some point near it, had to be the center of all celestial motion. If you were a natural philosopher, you thought that this was absolutely the case, and that any modifications to this idea that astronomers had made were just there to save appearances. Galileo's discovery of satellites around Jupiter, what we call moons now, just sort of demolishes this argument in its entirety. In March of 1610, Galileo rushes to publication a book he titles Sidereus Nuncius, or Starry Messenger, dedicating it to the Grand Duke of Tuscany, Cosimo Medici. The book produced an immediate reaction. Among the general public, at least the part that was literate, there was great excitement. Among the academic community, well, not so much. Galileo was accused of being a fraud and peddling optical illusions created by the lenses of his telescope. A key exception to this was the imperial mathematician to the Holy Roman Emperor, Johannes Kepler, who wrote a long review of the book that was broadly supportive of the observations and conclusions reached. One of the problems, apart from the quality of the lenses, is that telescopes can be really hard to see through. For anyone who has used a telescope for the first time, it can be hard to get your eye lined up just right so that the light traveling down the long tube passes through the eyepiece and into your eye in just the correct way. The smaller the eyepiece is, the harder it can be to do that. When I was the director of a small observatory in Kansas, we frequently had this problem, especially with older folks and young kids, until we had a lens donated to us that we called the TV screen, due to its size and ease of use. It was absolutely essential for us to be effective. Unfortunately, in Galileo's time, the telescopes had small eyepieces, which made them hard to use. Additionally, the mounts the telescopes were being placed on weren't very stable, which made them susceptible to being jostled. Galileo had to teach himself how to slow his breathing, much like a modern sharpshooter does, to keep his first telescope stable on its mount. So all of this combined to create a firestorm of controversy in the first few months after the book's publication. But then, confirmational results started coming in. The first was from Kepler, who had borrowed a telescope built by Galileo from the Elector of Cologne, and with 4 other observers, independently confirmed, both independent from Galileo and independent from each other, what the Tuscan astronomer had seen. More importantly, at least within Italy, a group of Jesuit astronomers also confirmed the observation, putting the question of what was being seen more or less out of reach. The issue now turned to whether the observations were of real things or whether they were just optical illusions. One of the problems that Galileo faced was he had no good theory as to how a telescope produced its images. In fact, what seems to be clear from his writings on the subject of optics was that he worked with an incorrect model of visual perception that made an optical theory for the telescope impossible. It would be Kepler, later, who would develop a complete optical theory that explained how light moved through a telescope and interacted with the eye to produce magnified images. The other was the already discussed entrenchment of an Aristotelian worldview that couldn't allow any part of the received wisdom of Aristotle to be wrong. And that probably was even the bigger thing that sort of frustrated Galileo's attempts to get his ideas into the scholastic community. Interestingly, the biggest focus of the arguments had to do with the moon's irregularity or lack thereof. Scholastics claimed that the moon had to be a perfect sphere for all of the reasons we've discussed in this and earlier episodes. Galileo responded with a variety of counterarguments, the most effective of which was to say that if the moon was a perfect sphere, it would reflect the light of the sun in such a way that an observer on the Earth would not be able to see it as a disk, but only as a single point of bright light. The irregularity of the moon, and by implication the other planets, was what allowed the light from all parts of the moon to be reflected into the observer's eye so that a disk was observed rather than a single point of light. For Galileo, the outcome of this publication was twofold. First, it vaulted him to a fame and notoriety experienced by few in the scientific community. Second, it produced an offer from the court of the Grand Duke of Tuscany, whom, in a move designed to curry favor, Galileo had named the moons of Jupiter after. While the salary offered by the Grand Duke was less than what Galileo might have made at Padua if he had combined a newly offered raise and his tutoring enterprise together, it freed Galileo from having to teach and offered the opportunity of significant additional patronage. In his last days there at Padua, before moving to Florence to take up this new position, Galileo made one additional observation of great importance. This was of Saturn, and it showed that there were some sort of additional appendages on the planet. We now know, of course, that these are Saturn's rings, but at the time, Galileo's telescope did not allow for good enough resolution to make that distinction, and so he described them instead as being like ears on the disk of the planet. This again called into question a number of Aristotelian assumptions about the nature of planets. Once in Florence, he quickly repaid his new employer's faith in his abilities by making a set of observations of Venus that are just absolutely seminal. What he observed was that Venus went through phases just as the moon did, and changed in size in a very specific way. In some ways, this would turn out to be the most monumental of his discoveries, and in other ways, it did little to resolve some of the deeper questions that were facing this whole enterprise. When you look at the 3 dominant models of the solar system, the Ptolemaic, the Copernican, and the Tychonic, the Ptolemaic model had a very different explanation for the observation of maximum elongation than the other 2 did. In the Ptolemaic model, the epicycle of Venus was fixed to a crystalline bar that kept it in line with the motion of the sun around the Earth, thus not allowing the planet to be seen any further from the sun than the 45 degrees or so you saw in the sky. In the other two models, the observation of maximum elongation was a natural result of the planet orbiting the sun and the limitations imposed on your observations due to that. Now, before the telescope, Venus remained little more than a point of light in the sky whose brightness changed, but that was otherwise unresolvable. However, with the invention and use of the telescope, that point was resolved into a disk, and that disk showed that the planet went through phases. Now, given the geometry of the models, the order and type of phases each model would allow could be determined and then compared with the observations that Galileo actually made. In the Ptolemaic model, the only allowed phases were basically what we would think of as a new phase and crescent phases. In the Copernican and Tychonic models, it was possible to achieve all of the phases, most importantly a full phase or nearly full phase of the planet, as it could physically be on the opposite side of the sun as the Earth was. Galileo's observations clearly showed a full set of phases, including that full phase, and a changing size of the disk of the planet that was consistent with what the Copernican and Tychonic models predicted. Moreover, the two together, the phases and the size, even explained the changes in the brightness of the planet very, very well. The result of this is, in fact, definitive proof of the incorrectness of the Ptolemaic model. What it is not, however, is definitive proof of the correctness of the Copernican system. Let's take a moment to assess this because it's important in a number of ways. First, for the physicists/natural philosophers, this shouldn't have been a real nail in the coffin for what Aristotle thought. I've read the work of a lot of people who talk about this observation, and almost all of them focus on the astronomy side of what it means, but very few of them seem to recognize that the natural philosophers are still working from an Aristotelian description that says that everything has to move around the Earth. While the astronomers might have been okay with Tycho's model, the scholastic natural philosophers were not. And this is the world in which Galileo is working. You can't be an Aristotelian, at least not a true Aristotelian, and believe Tycho is correct. You've got to go with Ptolemy, and Galileo has just produced observations showing that Ptolemy's model cannot be right. Second, while Galileo thus claimed to have proven that Copernicus was correct, that's a huge overstatement, especially for astronomers, most of whom have by this time switched to believing Tycho's model is more accurate than Ptolemy's. As Kepler will point out in a letter to Galileo, Tycho's model is able to produce the exact same planetary geometries as Copernicus's model does, and so the Venus phase observations don't resolve that controversy. This is a point that Galileo will never accept, choosing to believe instead that he had confirmed Copernicus and destroyed the Aristotelian paradigm once and for all. It is here that I'd like to make a couple of points to conclude this episode. Galileo, from this point forward, will begin to embroil himself in a greater and greater number of controversies surrounded in natural philosophy. He will also become a somewhat celebrated natural philosopher who will be feted in Rome for his work. Both of these things will come together to create a network of opposition centered in the frustrations of his academic opponents who see their worldview under attack from a person within their midst who uses unacceptable methods. Unfortunately, they're unable to counter his arguments effectively, at least at first, and so Galileo's influence grows. In time, these natural philosophers decide that if they can't beat him with philosophical arguments, maybe they can engage the authority of the church to help them. The early efforts at this result in abject failure and even an expression of censure from the church. But eventually they get questions about whether support of Copernicanism constituted heresy raised to the Inquisition. It bears repeating that until this point, there is no edict condemning Copernicus's work in any way, shape, or form. However, in 1616, the question finally does get put in front of the folks there in Rome. I'll leave the details out at this point, as I plan to do an entire supplemental episode on this issue. But suffice it to say that Galileo is completely cleared of any charges of heresy, but he is also told that supporting Copernican ideas any further would be unwise. Soon after, Rome issues a statement banning the teaching of Copernicanism and restricting the reading of Copernicus's book to copies where references to a moving Earth had been redacted or edited out. Interestingly, Owen Gingrich has determined that this process of redaction was only carried out in Italy and not in other strongly pro-Catholic nations controlled by the Habsburg family, such as Austria, Spain, and the Spanish Netherlands. It would be this restriction, however, that Galileo would be accused of violating in his publication of The Dialogue Concerning Two Chief Worldviews in 1632, an episode we will return to in due time. As we close, let me offer a few final notes. While we are not done discussing the life and work of Galileo, there are a number of events I have neglected to include in our coverage so far. For those who are interested in knowing more about Galileo, let me remind you of Stillman Drake's short biography of Galileo in the Oxford Very Short Introduction series, and David Wooten's Galileo, Watcher of the Sky. Both are excellent resources for those who really want to dig into what's going on here. A lot of great information in those two works. For those who'd like a more comprehensive and interactive introduction to telescopes, let me direct you to the Telescopes from the Ground Up site at amazingspace.org. They have a number of very helpful simulations and explanations that will help you see how lenses bend light and can be used to create telescopes, as well as a wealth of historical information regarding the development of telescopes from the period of Galileo on and onward. We'll put a link to the site in our episode notes on our website, thescientificodyssey.typepad.com. And for the educators out there who listen to the podcast, know that there are a bunch of great lesson plans associated with this site that you can use in teaching this material to your students. We'll also post some diagrams on the phases of Venus and how each model explains them, so you can get a better sense of what's going on with those. Next week, we celebrate our 100th episode, and coincidentally, our 2-year anniversary of the show. Now's the time to get your questions in so I can discuss them. Remember, while they can be about science and its history and philosophy, they don't have to be. You can ask questions about anything you'd like. About the only thing I won't touch right now is the third rail of politics, whether that be the U.S. presidential elections or the British Brexit situation. So I'll stay away from those. But you can send me anything else you want. I can be contacted via email by sending me a message at cldavies@mac.com, on Twitter @ChadDavies, by posting a comment on the website that I've given you, or by contacting us through the show's Facebook page. After our celebration, we'll take several weeks to look at the lives of Kepler and Galileo in some biographical detail, in an attempt to gain some perspective on the context in which their scientific work took place. After that, I want to spend at least one episode on the trial of Galileo and what it meant for the scientific community at that time and what it teaches us now. So until next time, full sails on your journey.